Okay. One of the unique things about a gas is the fact that it can expand or contract to any size container. And when it does that, pressure is involved. Okay, so like when you take a gas in a large container and put it in a smaller one, you're going to increase your pressure. So let's talk about some of these units and things related to pressure. So pressure is measured using a barometer. Okay, we've been doing this since the 1600s. One of the first people to create a barometer and use it to measure the pressure of air was Evangelista Torricelli. So one thing, remember the beginning of his name. Early barometer looks something like this, where you have a beaker filled with mercury in a very thin tube that has no air in it. And then what the pressure of the air does is it pushes down on the surface of the beaker mercury, and then some of it travels up into the tube. Okay. At standard air pressure, that height is usually 760 millimeters or 76 centimeters. Okay. So some units or measurements to remember related to what we consider the standard of pressure. Normal atmospheric pressure at 0 degrees Celsius and sea level is considered 1 standard atmosphere, or 1 ATM. Okay, everything else below this is an equivalent to 1 atmosphere. Okay, if you're using the metric system, that's 101.3 kilopascals. If you're using the English system, it's 1.27 pounds per inches squared, or PSI, for those of you that have ever filled a car tire. Or you can measure it in millimeters of mercury, or torr is just another way of saying millimeters of mercury. It's a unit given to honor Torricelli for his contribution to pressure. So, just something to focus on. Pressure is a force that is created by the molecules of the gas colliding with the walls of your container. So all of these units are in some way measuring a force per square area. Okay, so Pascal, which is a thousandth of a kilopascal, is a Newton per meter squared. Okay, so those are all metric units. Like pounds per square inch is all English units. Millimeter of mercury is the pressure or the force that supports a millimeter column of mercury. Atmosphere isn't per se a unit. It's more the standard for pressure, and we can convert all other units to atmospheres. And then just remember, a torr is exactly equal to a millimeter of mercury. So an application of gases is Dalton's law of partial pressures. Okay, so the total pressure of multiple gases is equal to the sum of all the individual gases. Okay, so total pressure is equal to the sum of the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and so on, until all of the gases have been contributed. So if you think about this, when we say that air has a pressure of 1 atmosphere, really that's coming from, 0.2 atmospheres of oxygen, 0.79 atmospheres of nitrogen, okay, and, all their small, minute pressures from carbon dioxide and helium and other gases in the air. So applying this to a problem, if you have a sample of nitrogen, oxygen, and chlorine gases that's combined to make a pressure of 2,312 millimeters of mercury. The pressure of the nitrogen is 765, and oxygen is 956, was the pressure of the chlorine. So pause this for a second, see if you can figure it out. So how I do this, so my total pressure equals 765 plus 956 plus pressure 3. So then I would just subtract 756 and subtract 956, and that should get you around 591 millimeters of mercury. Okay. Another problem you might see related to Dalton's law of partial pressures, where they give you percentages. And just like you would any other time you see a percentage, you just take your total and multiply by it. Okay, so 760 millimeters mercury times 0.2 for 20% is going to be 152 millimeters of mercury for your oxygen. Okay. So a way to double check, make sure this is actually working, if you do 760 times 0.8, that gets you 608 millimeters of mercury. And if you add that to your 152, lo and behold, you get your total of 760. Okay, so multiplying by the percentages works just fine. So, a common lab procedure is to have a reaction occur at the bottom of like a test tube or a larger like udiometer tube that is filled with water, and then the gas collects up at the top. Okay, so for example, we're going to do a lab where we collect hydrogen gas at the top of a udiometer tube that was at one point filled with water, and then the reaction takes place and replaces some of the water with gas. So, when this occurs, you have a gas in a closed container that is above water. Okay? If that's the case, then there's part of that gas is going to be water vapor or water gas. Okay, so it's going to be H2 and H2O gas. All right? Which means, in order to figure out the pressure of your H2 gas, you're going to have to subtract the water vapor. Sorry about that. Okay, so water vapor, how amount it is, depends on the temperature when you're doing the reaction. Okay, so on the next slide, there's this table, and it goes up by degrees. Okay, and as the water vapor, as the temperature increases, the pressure of that water vapor increases as well. Okay, so anytime you see a question where it's, reacted or collected over water, you need to go to this table, find the vapor pressure of the water, and always subtract that from the pressure of the gas you collected. Okay? So last thing to talk about is temperature. So there's 3 different things we measure temperature in. Fahrenheit is English system, not very useful. The conversion is very difficult, so we're not going to use that at all. Celsius is what our thermometers measure in, so we are going to have to know how to get from Celsius to what is called Kelvin, because equations are set up to use Kelvin. Okay? Big reason why Kelvin exists is because there's this absolute zero. There are no negative temperatures. Okay? In our calculations, if we use negative numbers or we use the number 0, it's going to screw up our calculations. So Kelvin makes it so that the coldest temperature possible is 0, so that means every other temperature we would deal with would have a positive number. The conversion is quite simple. You go from 0 to 273 or 100 to 373. All you do is add 273 to your Celsius temperature to get Kelvin. So, like there was a standard pressure, there's also a standard temperature. Everything that, equations are written for and things like that are for 273 degrees Kelvin, or the freezing point of water, 0 degrees Celsius. Those are equivalent or equal temperatures. Then, just in case you need to write it down, we will have to convert to Kelvin when we use temperature in an equation. There's no way around it. It doesn't work unless we do it. So remember, if you're going from Celsius to Kelvin, so you add 273. If you're going the other way, you subtract 273. Okay? And then just to kind of sum things up, whenever you will see this abbreviation quite frequently. So whenever a problem is talking about standard temperature and pressure, what it's really talking about is 273 degrees Kelvin and 1 atmosphere, but the rest of the numbers are things we can use to convert to those. Okay?